Pierce.
Could you do 21 from 5.2?
5.2, number 21. Sure. Okay. Use the form of the definition of the integral given in Theorem 4 to evaluate. Let's go back and look at what Theorem 4 says. There we go. Yeah. Okay. All right. So we're going to take 21 and we're going to start by converting that into a Riemann sum. So that's going to be the limit as n goes to infinity, the sum from I equals 1 to n of f of xi delta x, right? Where delta x is going to be b minus a over n. So in that case, it's going to be 5 minus 2 over n. And xi is going to be a plus I delta x, or in this case, 2 plus I times 3 over n, or 2 plus 3i over n. So far, so good. Okay, so we'll say the limit as n goes to infinity of the sum from I equals 1 to n of f of 2 plus 3i over n times 3 over n. And then remember that our f of x is just that. So we'll say this again then as the limit as n goes to infinity of the sum I equals 1 to n of 4 minus 2 times, and then 2 plus 3i over n times 3 over n. So far, so good. The f of x is 4 minus 2x. Oh. So I just plugged the 2 plus 3i over n into the x. So if we simplify there, we have 4 minus 6i over n. So those just kind of cancel each other out. And what I'm going to do now is I'm going to take this part and that part and pull it all out front of the sum. So that's going to be negative 18 over n squared. And I can do that because none of that stuff depends on I. I'm now going to go and figure out the sum from 1 to n of I. That was an identity that we were given in the book. It is n times n plus 1 over 2. And when I look now, I notice this is a degree 2 polynomial over another degree 2 polynomial. So the limit should just be the leading coefficient of the numerator over the leading coefficient of the denominator, or negative 9. I don't think you'd ever be expected to do that on the AP exam, to be honest with you. I don't think they'd ask you to use this definition to do it, because you'd have to memorize all those stupid summations formulas, and I don't think that's an expectation that they have.
So, on the AP test, what equation would we get?
You get nothing, but and they wouldn't ask you to do that per se, but what they would do is they would say would be reasonable for them to do is ask you to like be able to convert back and forth between those two forms. So if you have the integral, can you write it as a sum? Or if I give you the sum, can you translate it back into an integral? That's fair game. And I would ask you to be able to do the same thing. I would not ask you to evaluate like the limit, an infinite limit of a sum on a test, right? What we just did right there, where we actually found the answer, because I don't need you to bother memorizing these formulas, right? You have enough to memorize with your antiderivative rules and your theorems and everything else that has to be memorized for this course. It's not going to pile on some extra stuff that the AP doesn't expect you to memorize. I'm not going to expect you to either. Fair enough? Chanel?
That's kind of a stupid question, but why did it make you memorize all these formulas?
Because I'll tell you what, in college, no one's going to give you a formula sheet, ever. So in any of my math classes, I've never had a formula sheet or a formula given to me, unless it's like really an esoteric, like, oh yeah, like this, you need to know that this sum is equal to this thing or whatever. Where just like you wouldn't be able to, conceivably the derivation of this would fall outside of even the knowledge of this course kind of thing. But yeah, you don't get stuff. And these are like the basics, right? Like if you're going to take any kind of calc classes, it's pretty quickly they're going to expect all these things memorized also. I know. It's a lot. But here's the thing. You're doing a great job right now with your memorization. And that'll really, that'll really pay dividends. Like it'll be that much easier when you go to do it again. It's like, oh yeah, I remember this. Oh yeah, I remember that. Pierce, are you happy with what we did there?
Yeah, that makes a lot of sense.
Great. Who's next with questions from homeworks? Okay. Fair enough. Just to give you a little idea of where we're at. So we looked at this idea of an antiderivative, was just basically, can we go backwards from a derivative and recover a function that when we differentiate it would give us the same thing, right? Now, how many of those functions did we find there are? Infinitely many, right? Because of the plus c at the end.
Well, so I actually did have I lost my notebook at home, but
Yeah, go ahead.
it's from like 4.9. It was like when we were using our calculator to find when we had the answer, and it was minus y1 answer divided by y2 answer. It was asked.
Oh, so that's 4.8,
Oh,
right?
Okay.
Yeah, because that sounds Newton's method-y.
Yeah, it was asking us how to find all of them. I didn't know how to find all.
Okay.
I tried to look through our examples.
Yeah, let's see here. So Newton's method, 7-11. Well, probably weren't those ones, right? Um, 15, negative root of this thing, probably not that. 17. Find all roots. Oh, sure. So let me grab one of those. So we have something like this, right? Where the directions say find all roots for the equation.
Yeah.
Okay. So let's just do 17 for an example. All right, so let's think about really what this is going to look like just real quick. So if I graphed cosine 3x, that's going to look like this, right? And if I graph x plus 1, that's going to look like, you know, something like that, right? So just from an eyeball standpoint, it looks like you're probably not going to get more than 3 solutions out of this. And any solutions I find are going to be relatively close to 0. Because when I get out real far, obviously that's going to be way above or below our cosine function, right? Okay. So for example, like once we get past positive 2, right, x plus 1 is greater than 3, so it can't intersect cosine anymore. And once you get to the left of like negative 4, you know, it's less than negative 3, so you can't run into anything out there. So everything has to be between negative 4 and positive 2, right? All of our solutions are going to lie in there. So I'm going to use that a little bit to help with my guesstimates. So we'll set up our f of x. So I'm going to just have 3 cosine x minus 1 equal to 0. So this is my f of x. So the derivative of f of x is going to be negative 3 sine x minus 1. So we're going to start doing some Newton methods. Let's just start with x equals 1 as our initial guess, right? So I'll just call that xi or whatever. So xi plus 1 is going to be xi minus f of xi divided by f prime of xi, right? That was the formula. So let's go ahead and set this up on our calculator. So we have positive 3 cosine x minus 1, and then negative 3 sine x minus 1. Exit out of there. We'll do 1 as our initial guess, and we're going to do the previous guess minus alpha y equals, we'll do y1 of that previous guess over y2. Oops. Pressed the wrong thing. Forgot to go to y bars. Y2 of that previous guess. And we'll just kind of rattle off some here. And I think at this point we got 6 decimal places there for one answer. So I'll just call this like solution 1. And that was, I'm going to just put it over here for a second so it's easy for me to write it, 1.98817. Oops, I guess I need to press one more enter to make sure that it's, 5. Well, I guess they round to 6. Okay, so that's one answer. That's pretty close to 2, right? So I'm going to do this again. This time maybe I'm going to guess 0.5, though, as my initial guess. See if I can get a different result. Since I know that 2, like this solution is at like the very right end of what is going to be feasibly possible. So I'm just going to do the same thing with 0.5 now as my starter and see if I get something different. I'm not, so I'm just going to stop. Let's maybe try 0. and see what happens there. Nope. That didn't do any good. Let's try negative 0.5. That didn't work either. Okay. Try negative point or negative 1. So I'm just going to kind of keep, oops. I'm just going to kind of keep moving down the boogers. All right. Give me this thing from like way back up here before I screwed it all up. There we go. And I'm just going to oh, that is interesting. Do I have the wrong setup here or something? Did I do something dumb? Let's look real quick. No, that's okay. Okay, well, I don't know. Let's go to negative 2. We're coming in from the wrong end here. Interesting. Negative 4. Is this just broken? Am I doing something wrong? I'm not sure. Yeah, it's very bizarre. Well, let's do like negative 8. Let's get silly, right? That's way outside. Nope. Just being really sensitive here, huh? 0.1. Nope. Yeah, that didn't do it. What are the, oh, all right, let's cheat a little bit then, Braden? So I'm just going to graph this real quick and look at what the actual answers are supposed to be. Oh, I know why it's not working. Look at this. How dumb am I? That makes a heck of a lot more sense. And now I bet if I did like 0, because that answer before is probably wrong. There we go. There we go. So that's an answer. That makes a heck of a lot. I was like, why am I keep getting one value? This doesn't seem like it's working. And I just was doing the dumbest thing possible, which was you didn't check the mode of your calculator there, Mr. Smarty Pants. Okay, maybe try 1. That didn't work. It gave me the same value. Try negative 1. That's going to work. That's giving me something new. So negative 1.862365. I can't remember anything. 62365. 62365. Okay. Maybe try negative 2. Again, I don't really know. Actually, that's probably not big enough. Maybe we'll try negative. Yeah, I'm going to do negative 3 because this is awful close to negative 2, right? If I do that again, I'll probably just end up getting that one again. It's probably not far enough away. Let's do negative 3. Yep, you're dead on. So do that again. That looks good because now we're decreasing down to that looks great. Negative 637958. Negative 36 something, 66 something. 637958. 637958. And that probably does it, right? Does that feel better?
I'm just confused, like if there was like, I had to do some algebra to find something. Or...
I think had we thought about what this was going to look like and knowing like that's where I'm guessing from, I think makes a huge difference in like, okay. Yeah. And even this picture where it's like, okay, I should probably have 2 negative and 1 positive. Yeah. Like super helpful in terms of like, okay, Give me a guess.
I got the positive one, and I just didn't know how the book got the other.
Yeah. So just different guesses for our initial, but nothing really changes otherwise, right? Okay. Okay. So just a little catch up at like what we've done so far, right? We started with this idea of an antiderivative, right? We saw that that was relatively easy to do because it's just using our derivative rules in reverse. Now there's infinitely many antiderivatives for a given function because all you have to do is tack the plus c at the end, and c can be any constant. So like, the thing plus 1 or the thing plus 2 or the thing plus 3. Easy to see that. In the next section, we saw somehow this was going to be related to this idea of the area under a curve, because when we talked about like a velocity function and a position function, like if I take the graph of the velocity and like I just constant velocity for 10 hours to get the distance traveled, it's just the time times the velocity, which is like the area under that curve. So like intuitively, this is somehow going to be connected. So we spent some time then developing how to calculate the area under these curves. And what we started with, or what we did was you took this idea of, well, if it's not a like straight line curve where it's not something I can composite into like rectangles and triangles and trapezoids and stuff like that, I can't calculate the area exactly, but I can approximate it really well with some rectangles. And that's what we call the Riemann sum. We're like adding up these rectangles. And we talked about you can do that using like the left end of your interval or the right end or the midpoint or whatever. And they're all going to be approximations. And ideally, if you take those rectangles skinny enough and you do enough rectangles, you get exactly the area under the curve. And that's what we saw in 5.2. And then 5.3, these two ideas came together. That was the fundamental theorem of calculus that says that, okay, if I take the derivative of an integral, that just is the function I'm integrating. Like derivatives and integrals kind of cancel each other out. And then if I want to do a definite integral, I can just, instead of calculating the area under the curve, I can do the antiderivative of the function evaluated at the upper bound minus the antiderivative of the function evaluated at the lower bound. And I don't have to mess around with any more limits and sums and all that stuff goes potentially, right? Now, depending on what you're given, like if you're given a graph, you can't exactly calculate the antiderivative for a graph. That's not. But if you have an equation, there's a lot of times you can do that. That's what we saw in 5.3. Today we're going to look at 5.4. So up until this point, we've been talking about definite integrals. So like the integral from a to b of f of x dx. Remember, that's just a number. That is the area under the curve from a to b, right? Number. What we're going to talk about today is an indefinite integral, which is a function. So if I write the integral of f of x dx and there's no bounds on there, what it's looking for is the general antiderivative, which is exactly what we did in 4.9. So the key to remember, definite integral where we have bounds on our integral symbol, that's a number. It's just f of b minus or antiderivative of b minus antiderivative of a. Indefinite integral, no bounds on our integral symbol, is a function of x. Just like when we take the derivative of f of x, we get a function of x. When we take the indefinite integral of a function, we get a function in x, right? So for example, if I do the indefinite integral of x squared dx, that's going to just be x cubed over 3 plus c. The indefinite integral of x squared, where I've added 1 to the exponent and divided by that same exponent, and then plus the c. And I know that that is the solution because if I differentiate x cubed over 3 plus c, I recover x squared. So just same idea as 4.9, right? We're just adding a symbol to say this is the symbol for do the general antiderivative. Now we're going to just information dump a bunch of formulas here. Should you memorize these? Yes, but guess what? You already memorized them because all they are is your derivative shortcuts in reverse, essentially, right? You know, like I know that the derivative of negative cosine is negative of negative sine. So if I integrate sine, I should get negative cosine, right? So it's just really the same as these derivative rules you already have been memorizing. They're just recast in the other direction with maybe some little slight adjustment so it's like not as silly, like we're integrating sine rather than negative sine or whatever. And then I crossed out the two hyperbolic trig functions because we haven't talked anything about hyperbolic trig functions. We're not going to talk anything about hyperbolic trig functions. I've never talked anything about a hyperbolic trig function. So I crossed those out.
Is it out of the scope of this course?
Yeah. Okay. So let's go and do some practice here. All right. So here we're asked to do the indefinite integral. I can tell it's indefinite because there's no bounds on my integral symbol of 10x to the fourth minus 2 secant squared x dx. So I'm going to do this showing a lot of work the first time, and then we're going to cut down on the work kind of in the future as you kind of get a feel for like how this is going to go and like what stuff kind of matters and what stuff doesn't. So the first thing I would do is I would distribute my integral symbol across this function because I know integration, differentiate, distributes across addition and subtraction. So I'd have the integral of 10x to the fourth dx minus the integral of 2 secant squared x dx. Everybody's good there? I'm going to use my property of integrals because I know I can pull those constants out to the front. Everybody's good with that? And now I'm going to use my antiderivative rules. What's the antiderivative of x to the fourth? And plus c. Okay. And then the antiderivative of secant squared is? Yeah, let's call one of these C1. I'll call the other one C2 because they might not necessarily have to be the same number. Should know.
Wait, so how come in the last lesson we didn't have to put the plus c, but this one we have to?
Because in the last lesson, we're not finding a function, we're finding a number. Okay. Right? The definite integral is a number, so there's no plus c at the end. It's a number. It's like 7 or 15 or 12. Indefinite integral is a function. Now that function could have plus a constant that just evaporates when we do the derivative that we can't know for certain, but there could be like a plus 2 or plus 7 or minus 8 or something at the end of it. Is that okay? So we've done the antiderivative. Let's distribute through our constants. Oh yeah, thank you. Thank you. Everybody's okay there? And now what do I get if I do 10 plus C1 minus 2C2? Yeah, just going to be a new constant, right? So we'll just put a plus C on at the end. Now, in practice in doing this, nobody is going to write those there. They're just not going to write them, and they're just going to put a plus C at the end because they just, you just aggregate those constants together into one constant. 2 times a constant is still a constant. 10 times a constant is just some constant. Like we just aggregate all that stuff together, and it's just one thing. We'll just call it plus C.
But why is it just C? Why isn't it 8 with 10 minus 2?
Right. So let's say C1 is 5, or let's say C1 is 1 and C2 is negative 1. If I add those together, I'm just going to get another number, right? That's all we're saying. Because they don't have to be the same number, right? So there's just a number, right? Which is all the constant, 10 times a constant, still a constant. 10 times a constant minus 5 times some other constant, still just a constant. So we're just going to aggregate it all together and call it C because, quite frankly, we don't care. And it doesn't matter.
You wouldn't be able to find out what C
And you cannot find out what C is without some other piece of information, where if you have to say f of x equals this, and f of 2 is equal to 5 or something. If you have this piece of information, now you could solve for C. Because once we have our function for f of x, we can plug in 2 and then equals 5 and then solve for C. But without something like that, there's nothing you can do to find C. So whether you write it as, 10 times C1 minus 2 times C2.
Would they give us capital F2?
Well, I just called that the integral is equal to f of x, right? So when I do the integral, when I plug 2 in, I better get 5 out. So that's what will allow me to solve for C. It doesn't really matter. I mean, if you want to call it cap F, you could call it cap F, or they probably wouldn't. But that's what you'd need in order to solve for C, is you need some other additional piece of information, like when I've done the antiderivative and I evaluate it at some specific x, what y value does it have to have? Okay. How about this one? Hi, Talika.
I was making blankets for.
Oh, that's kind. What about this one? If I look at this, what should I do?
Maybe try a trig one.
Yeah, so if I look at this, there's no antiderivative that involves cosine over sine squared, right? And in fact, none of my antiderivative rules even involve division other than something like, these three. And none of those three even are close to looking like what I have there. So as it's currently written, there is no antiderivative rule that applies. So we're going to have to do some algebra to massage this into look like something we need. Chanel's right on the right idea. It's going to be a trig problem. I'm not going to use that one. I think what we'd be better off doing is thinking about it this way. You guys see what I did there?
So that would be cotangent, and that one would just be cosine inverse?
Cosecant.
Oh, cosecant, yeah.
And now this is that one of my antiderivatives. Yeah, that's supposed to be a time symbol. My apologies. Yes, it is, right? Let's go back and look. Look, it's right here. It's negative cosecant x. If you remembered that one, good on you. A lot of these ones I always struggle, and I end up having to do the antiderivative in my head to double check that I did the right one. Does that feel okay? Now, this is going to be a familiar theme throughout the rest of the year. Very often you're going to be given to integrate something that there is no direct antiderivative rule for, that you're going to have to do some algebraic massage to what you're given to make it fit into something you can do the antiderivative for. Your biggest indicator that that's what you're going to need to do is if you have multiplication or division going on, right? If you have two functions that are being multiplied or divided, There's probably going to be some algebra that you need to do to kind of like massage that into a form you can do an antiderivative with. And as we go, we're going to build out more and more algebraic tricks to do some of that stuff and talk about like, okay, if it looks like this, we can use this trick and try to like cram it to look like a inverse trig function. Or I can do this other trick to kind of cram it to look like a logarithmic function. But at the end of the day, there's some things that just like you don't have any tool to do. And the AP is still going to expect you to be able to do something with them. And we'll talk about that here in a moment. Let's do this one first. What's different about this one than the previous one? It's a definite integral, right? Okay, so if I do the definite integral, the antiderivative of x cubed is? You guys should have all been able to answer x to the fourth over 4. And the antiderivative of 6x, again, I can ignore the negative 6 and just do the antiderivative of x. Good. And then usually the convention would be to draw a vertical line there and write the bounds on it, saying that we're going to evaluate this from, 0 to 3.
Do you then just use that law from last?
No, I mean, I just do, this is what we're doing. Yes. Yeah. Now, the number one place where students make mistakes when doing this by hand is they forget to distribute, because this whole thing is like my cap f of 3, and this whole thing is my cap f of 0. So that negative sign needs to distribute. Now, you're not going to be punished on this one if you miss that, because, well, f of 0 is just 0. So there's not really like any big deal here. So what do we have? We have 81 over 4 minus 27. If I make a common denominator, that's going to be 108 over 4. And then, so that's going to be negative 27 over 4. Is everybody okay with what I did there? You want to hear some great news? You can do this problem all on your calculator. All of you can do this problem all on your calculator. In fact, any definite integral can be done all on your calculator. Let's show you how to do that. If you have a calculator with you, I invite you to take it out and follow along. But this is good stuff. So the way I like to do this is I like to call this stuff just like f of x, and I'm going to put that into y1. So into y1, I'm going to do x cubed minus 6x. Now, it's not critical that you do it this way. I'll show you how to do it without using the y1 in a second also. But often I like to do it this way because many times I'm going to be doing like lots of things with the function. So if I have to like plug something in later, or I have to do the derivative of it and plug something in, it's often just helpful to have it in one spot so I don't have to type it in over and over and over again, especially if it's something complicated. This isn't terribly complicated, but all right. So then I'm going to go back to the main screen here. I'm going to press the math button right below your green sign or green alpha button. I'm going to scroll down to command 9, which is fnint. That stands for function integration. And I'm going to press enter. Whoa, look at that. So all I'm going to do now is just type in so it looks exactly like it does on my sheet of paper. So I'm going to do the integral from 0 to 3. And then inside the parentheses, I'm going to put my y1, which is where I typed in my function. So I'll do vars, yvars, function y1. And then with respect to x, and then press enter, which is the same thing as negative 27 over 4, right? Now, alternatively, instead of putting the function into y1, I mean, you can just type it right inside your integral directly. That works also. You can do it that way. But every definite integral can be done on your calculator. And in fact, on the AP exam, you will probably run into multiple questions that are impossible to do a definite integral by hand, where they expect you to just type the stuff into your calculator and get the number. Happens quite frequently in the free response questions. Which is wonderful, right? Isn't that lovely, lovely, lovely? Yeah, it's like free points. You have to remember that you can do it. All right. Try this one. Yeah, 0 to 2. Yeah, do it in your calculator if you want. Yeah, it's going to be a crazy decimal. That's normal.
Mr. Cool, I think my calculator crashed.
Oh no.
Yeah.
What happened? What's it doing?
I pressed enter. Yeah, no, it won't even turn off.
Here, come bring it, show me.
Oh wait, no, error.
Okay. What's in your y1?
It said 2x cubed minus 6x plus 3 divided by x squared plus 1.
Now, did you write it as 3 divided by x squared plus 1? Or did you write it by like this?
I put a parenthesis. Oh.
Because if you didn't do this one, that's probably why it crashed. Because the other one is like would be a ridiculously hard integral.
Yeah, I put the parentheses around 3, just 3 and x.
Yeah, not good enough. It has to be around the denominator. Or if you did like the alpha y equals and pick the first option, you put in the horizontal fraction bar so you don't have to worry about your parentheses. That's the way I like to do it.
Was the answer like negative 0. Yeah.
Everybody feel okay with that? Again, on the AP exam, if you're in the calculator active section, you should not be doing any definite integrals by hand. Right? If the calculator's active, do that stuff on your calculator. Don't waste the time to do the antiderivatives and plug it in and then type the stuff into your calculator to evaluate. If it's the non-calculator, well, what else are you going to do, right? That's all you got. But on the calculator sections, don't do any definite integrals by hand. Okay? All right, let's do the next one. Now let's try doing this one by hand. Okay? Because this is definitely doable by hand.
Is it?
When you look at it, though, it looks rough, right?
You could separate the fractions.
Yes. So Chanel's dead on. You want to separate that into 3 fractions, all with a common denominator of t squared. So you'd end up with 2 plus t to the 1/2 minus t to the negative 2, right?
Oh, yeah.
So my antiderivative would be 2t plus t to the 3 over 2 over 3 over 2 minus t to the negative 1 over negative 1. Evaluate from 1 to 9. Is everybody okay with how I did the antiderivative there? So 2 times 9 plus 2 times 9 to the 3 over 2 over 3 minus, let's see, 9 to the negative 1, plus 9 to the negative 1, and then minus 2 times 1 plus 2 times 1 to the 3 over 2 over 3 plus 1 to the negative 1. Or you just type that through on your calculator and you get let's see, what does it say here? 32 4/9. I don't know why they decide to write it as a mixed number. Oh, I see why. And again, even on a no calculate, like a test where they want more than that, I would do this part by hand, but to get this number, I'm typing that thing into the calculator from get-go, right? Like if it's just like a regular test question and like I say, show your work, like I'm going to do up to here by hand, but this number, I'm not going to type that into my calculator. That's too much symbols to type in. I'm just going to do that part on my calculator and write the number because it's way less typing. I'm way less apt to make like a stupid negative sign mistake or something. You know, like if I'm convinced I've written down my work correctly, typing that into your calculator stinks, right? If I was dead set on doing it that way, even the way I would do it is I would type my general antiderivative into y1. And then I would do vars y vars function y1 of 9 minus vars y vars function y1 of 1. Because I feel a heck of a lot better about that work. 34 4/9? Oh, what did I do then? Uh-oh, SpaghettiOs. Where's the problem? You did y1? Oh, I bet it's... Yeah, look at what I did. Oh, no, that's right. But this should be plus, right? Minus a negative. That's the problem. There we go. My apologies. See, even better reason just to type it in from the beginning and let the integral calculator do the integral for you. Like I can handle the work and I'm confident I can catch my mistakes there, but like getting that thing into the calculator or into the, can be a problem sometimes. Okay. All right. So let's look at some application now, right? So we remember that the fundamental theorem of calculus says that the integral from a to b of f of x dx is the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a, right? Remember, cap f is the antiderivative of b is just evaluating at b. So that means then that the derivative of capital F should be just a little f, right? So if I integrate the derivative of cap f, that's the same, doing the same thing. right? If cap f and little f are the same thing, then these things are the same thing, right? Where this comes into play, remember that we have position and we have velocity and we have acceleration. So what that means is that I can take acceleration and recover velocity from that, or I could take velocity and recover position from that. Just like if I had position, I can differentiate to get the velocity, and if I have velocity, I can differentiate to get the acceleration, right? So let's look at an example here. So it says a particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6, where velocity is measured in meters per second. Part A says find the displacement of the particle during the time period from 1 to 4. And then part B says find the distance traveled during that time period. What the heck is the difference between displacement and distance traveled?
You can travel, like go backwards and then forward again, and then you travel farther.
Yeah, so like, imagine we did something like that. This is the displacement, but the whole length of that path is the distance traveled, right? So displacement is just the position. So that should be the integral from 1 to 4. Why 1 to 4? That's the time period for v of t, right? dt. So that's going to be the antiderivative of t squared minus the antiderivative of t, minus the antiderivative of 6, and then evaluate it from 1 to 4. So that's going to be 4 cubed minus 3 minus 4 squared over 2 minus 6 times 4 minus 1 cubed over 3 minus 1 squared over 2 minus 6 times 1. And that stinks. I don't want to deal with all those fractions, right? Yuckarooskies. Let's cheat a little, and that just comes out to be negative 9 over 2. And then I guess the unit there should be meters, right? So it means that we actually ended up somewhere over here. Does everybody feel okay there? Now let's think about, oops, that was my start. That's like my end. So let's think about what we would need to do to find the distance traveled then. So the problem is like this section here, right? What is the velocity when it's in that, for that section? It's negative, right? So what we'd like to do is find a way to like, just think about that velocity as something positive, because then if we do the same thing, we just get the length of the path, right? Is everybody okay with that idea? So what are we going to have to do to this to get the, to make that velocity always positive? Yeah, good. Everybody feel good there? Okay. How do we integrate an absolute value? All right. Well, here's my question for you. If I look here, do any of these give me a shortcut for an absolute value function? Well, we're not integrating an absolute value, right? The absolute value is in the answer. It's not from the start. So that's a little bit tricky then, right? So guess what we have to do? We have to go back and think about what's actually going on. So let's say this is our v of t axis. And remember that that's our velocity function, right? If I factor that, should be this. So I know at like -2 and at +3, this function has got zeros, right? Does this parabola, and it's a parabola because it's a degree 2, does it open up or open down? Up. How do you know? The leading coefficient is 1, or is positive, right? So we know it's going to look like that. Everybody agree? So we're worried about from 1 to 4. What part of our velocity function is negative from 1 to 4? From 1 to 3, right? And what part of our velocity function is positive? 3 to 4. So what we're going to do then is we're going to go, okay, well, and we're just going to chunk it into the part that we know is, oops, forgot my dt. The part that we know is positive and the part that we know is negative. Or I should say negative and positive. We wrote the negative part first. Okay? So I know from 1 to 3, v of t is always negative, right? So if I did the absolute value of f of x, that should be negative f of x when f of x is less than 0, right? I have to do the negative of it if it's negative, because it'll make it positive. And we know it's positive f of x if f of x is greater than or equal to 0. Now we know that in this piece, v of t is always negative, right? And in the other piece, we know v of t is always positive. And I know that with my rules of integration, I can just pull that negative sign out front. So I have negative, and then I'll do my antiderivatives again. So I can do that, right? Do my integrals. And now I'm going to have, when I plug things in, so like that's my work to evaluate it, right? Now on an AP exam, if it's a non-calculator, you could be done at this point. You don't have to grind that out. You could just like, I've done it. That's a number. It's on you to figure out if that number is the right number or not. But like, I did the antiderivative. I made my substitution. I've taken this as far as it needs to go. The rest of this is like, like middle school math reality, right? It's a hard middle school math problem, but it's middle school math. You don't need to show them you can do middle school math. Now, if we really want that number, it comes out to be about 10.17. And if you have your graphing calculator, again, once you've gotten it to like that spot, you could use your graphing calculator to integrate that, right? I would not do it by hand. I'm never going to do a definite integral by hand if I'm allowed my calculator. I'm just going to let the calculator handle it unless the directions specifically ask, like, show all of my work. In which case, I'm just going to use it as a checker. Then I'm still using my calculator to do it because at this step, I'm not doing that stuff by hand. I'm just typing in my calculator and pressing, doing the integral. Does that feel okay, though? Yeah, the trick is that anytime you want to integrate an absolute value function, you have to chunk it into negative parts and positive parts, and then you negate the negative parts to make them positive, and you're good. Right? But that's the trickiest part, is figuring out how to do the chunking. Does that feel okay? And that's a clever thing. Like, it's hard to come up with that on your own without having seen somebody do it before. And it's like, oh, that's neat. That's clever. That's exactly what you need to do. Because it lets me drop the absolute value now. And now it's something I can do the antiderivatives with. All right. Last example here. It says figure 4 shows a power consumption for the city of San Francisco for a day in September. P, that's the y-axis, is measured in megawatts. And T, the x-axis, is measured in hours. Estimate the energy used on that day. Energy is just going to be power times time. So what are we really going to do to estimate this? I'm counting rectangles here, folks. I'm counting rectangles, which is like super tedious, right? But like, for something like this, that's 0.5, maybe that's 0.1, 0, 0, 0, like 0.6. And I'm just kind of like estimating anything that's on a boundary just to the 10th. And everything else is just a straight count. But that's literally what I'm doing. And I think there's probably a unit conversion going on here because I have a feeling that megawatts are probably measured per second or something. So there's probably some annoying conversion to get this into joules. But I'm not worried about that because, quite frankly, like, that's a physics problem, not a calculus problem.
Isn't it just like watts per second?
Yeah, so there's like a unit conversion between megawatts and hours that you have to do to like get that into joules or whatever, but like, I don't care. The idea here is just that like we're counting rectangles to approximate an integral. If you're on the AP exam and they give you something, some function, and there's a grid laid behind it, and you're asked for an integral and you're not given the equation for the function, how are you supposed to approximate it? You're counting boxes. Just counting boxes. The one thing you have to be careful about is making sure that the boxes underneath the x-axis are negative boxes. Right? You have to remember to do that, but like literally just counting boxes. So it's not too bad if there's anytime you see a function with a grid laid under, like over top of it, and there's an integral involved, probably some box counting going on, which is okay by me because I'm pretty good at counting. So that's it. That's the idea. So again, I think this section, not particularly difficult, right? There's some tricky things that we saw, but they're all just tricks, right? Like, how do I deal with an absolute value? How do I do some algebra to manipulate this into like a form I can use my antiderivative shortcuts on? But like the ideas here are just ideas we've used. Like it's just rehashing. The big concept is just doing stuff we've already done, which is okay by me. As far as second semester goes, I think we've climbed like the theoretical mountain. From here, we're just going to be like doing application, kind of sliding our way down, kind of hitting application after application after application. We're going to be tying back in ideas from first semester as we do that, because you'll start seeing like, okay, say g of x is the function, something like this, and ask to find the maximum value or the minimum value, or where is it increasing or decreasing, or concave up or concave down. So you're still going to end up with those same kind of first semester questions. There's just now going to be like an integral inside of the function that you're asking to find like a maximum or minimum or increasing, decreasing, concave up or concave down. Everything works exactly the same though. Because what's the derivative of g of x look like? Actually, that should be like that. So if I want to find maxes and mins or increasing, decreasing, I'm just setting that equal to 0 and solving, right? If I want the second derivative, if I'm looking for concavity, and then I'm just setting equal to 0 and solving, doing the same types of things that I did first semester. It's just now that my function might have an integral sticking in there. But it's okay. It's okay. It's not bad. I can do that. All right. So that's kind of where we're going. So we'll see some of that stuff first, and then eventually we're going to like looking at like calculating volumes via integration, or like area between two curves. Stuff like that, which is fun. Chanel.
This is not due until next Sunday.
Correct.
Okay.
This is not part of this Sunday's problem set.
But it's on the test.
But it would be on the test. I know. Boo is right. I've gone and put in some multiple choice and free response questions for you guys to practice. We're going to talk about some of these things in class on Monday next week. We'll have like a review day, and we'll break you guys up into teams, and we'll have a little contest, and we'll do some of these multiple choice and/or free response questions. After that, I'll put a key in for those things because I've worked the key out. But I want to like let you guys try to do stuff and have it be kind of fun and competitive for a day, just for something different. Sure.
Yeah.
100% test?
No.
Automatic 100%.
Not an automatic 100%, but
What about a candy?
we'll find something fair.
Would
Yeah.
the 4, 8, the like 5 and 12, whatever, would that be a test?
So I wouldn't have something that involves like that much guessing, because it just is a time suck, right? Like I would have the kind of Newton's method problem I would invent for you would be something with one solution.
Okay.
That's relatively going to be like almost idiot proof in terms of your guess, to just like, do you know this formula? Can you do this on your calculator? Can you write down some intermediate guesses, those intermediate values along the way to give me something that's, relatively easy. So it'd be like, here's this function, find the solution, correct to 6 decimal places, write down your 5 intermediate values that you get from the calculator. You don't have to show me the setup and do everything else on the calculator, So I'd want to see the derivative. I'd want to see the general form of it, how you've written it down, and then let the calculator handle it all from there. Whoops! It's an expensive cup to be dropping like that. Chanel.
So is are the MCQs and FAQs like pretty representative of the test? Or,
I should get something up for test format here
okay, good.
soon.
Okay.
I just, to be honest with the missing 2 days I was home, I didn't have as much time to like, when you're home and like you have a 4-year-old that you're also dealing with, like there's not as much time to like sit down and do the same kind of things that I do at school, believe it or not, when I have to teach and everything. But I should have something for you by Monday.
Okay, that's fine, that's fine.
This is off topic, but do you think we're gonna have a snow day tomorrow?
I am not privy to those kind of conversations. I was not even aware that they were expecting that kind of snow tomorrow.
I mean, it's not supposed to stop until tomorrow morning, and Mr. Coolidge today ended up in a snowbank when I was driving.
Okay, as a reminder to all of us newish drivers, when we're driving in snow and we're making a turn, no gas, no brake.
I know.
Like, do all your slowing down and speeding up in a straight line. All those things are light. Coast through your turns. Everything tends to be okay. Once you've finished your turn and your wheels are straight again, then you can start adding some gas. But you brake with your wheels straight. You gas with your wheels straight. Try not to have your wheels turned when you're doing either of the other two, and things tend to be okay.
Everything was fine other than the snowbank.
Yeah. Just as a reminder, because you don't talk about this in driver's training, which is a useful thing to have to talk about, more so than like, you know, the speed limit on a unmarked rural road or something. 45.
You literally haven't been like a real snow day, so I think we should We've gotten home from I think it was
I know.
on Friday, Tuesday, Wednesday.